All right, let's go ahead and get started today by taking a look at your homework. A little bit of a longer homework assignment, shorter homework assignment tonight over the 3-day weekend. We have questions 1 through 12 on page 67, and we're going to take a look at those. Good. Kendall's looks much more thorough. Not comparing right. Oh, okay, never mind. Audrey wins. All right. Audrey wins. Well, she was present though, so she did have to do it. So. All right. Let's see. Number 1, the 5 main components of air. It says constituents of air. When it has maximum concentrations of water vapor and carbon dioxide, list them from highest to lowest concentration. What did you have, Michael?
The 5 main constituents of air are water vapor, carbon dioxide, ozone, sulfur dioxide, and nitrogen dioxide.
By main constituents, main components, I think it meant the main things that are in the air. This would have come from a little table there. Kendall?
That's what I put actually.
That's what you put as well?
It's down at the bottom, gases of variable concentration.
Oh, okay, no. Okay, so if carbon dioxide's at its max, then it's at 7%, right? So, or water vapor is at max at 7%, which would put it 3rd place. Because nitrogen's in 1st place, oxygen's in 2nd place. Water vapor at its peak would be in 3rd place. And then after that would have to be argon. And then if carbon dioxide's at its peak, it's going to beat out the neon. And it's going to beat out ozone. So carbon dioxide would be the 5th one. So do you see how you're actually kind of using both parts of the list at once? Yeah, okay. Anyway, let's move on. The main ones are, honestly, is nitrogen, oxygen anyway. The others are in such small percentages, it's negligible. Number 2, what causes air pressure in a container? And let's go back to Michael.
Vacuums cause air pressure. Yeah, no, now that I'm not sure what I read.
All right, so Kendall, what did you have for number 2?
I said when molecules are heated, they increase in energy and move faster, and when gas molecules are moving, when they move faster, they collide with more force in a container and condense.
Okay, Audrey, what did you have for number 2?
I had something to do with atmospheric pressure.
We're just looking for temperature and number of molecules cause air pressure in a container. Right, higher temperature, or the temperature changes in the number of molecules causes the air pressure in the container, the bombardment of molecules in the container. Number 3, what determines the strength of air pressure at sea level? 3rd tries the charm.
Gravity.
Gravity, right? The weight of the air. But what did you write for your actual answer?
Gravity determines the strength of air pressure at sea level.
Yeah, and since gravity at sea levels, well, again, depending on sea level, where you are in your latitude, I guess that would change it a little bit. But yeah, it's just the weight of the air molecules that affects that. Number 4, this is a funny answer. What demonstration was staged by Otto von Guericke, and what did he show by his demonstration? Talked about it yesterday and looked at a video of 2 guys doing a mini version of his demonstration. Kendall, how did you describe it? Story time with Kendall.
The demonstration by Otto von
Guericke
was he joined 2 rims of 2 copper hemispheres into a sphere, sealed it airtight with a ring soaked in wax and oil, sucked the air out of it, and tried to get 8 horses on one side and 8 horses on the other to pull them apart. He demonstrated atmospheric pressure through this cycle.
Very good answer. That was well described. Was that copied from the book word for word?
Yes.
Okay. I'm going to say your summary was very clear. And you just copied it down. Well, you know, okay, that's one way to be thorough. All right, number 5. What laws pertaining to fluids assume uniform density? Audrey?
Archimedes' principle and Bernoulli's principle are laws of fluids that assume uniform density.
Actually, it's the other ones. Those 2 don't have to assume a uniform density, which is why they will still apply, as we'll talk about today. So it would actually be the other laws. So Michael, what did you have for number 5?
The law of liquid pressure and the principle of continuity assume uniform density.
And Pascal's principle as well. Assume uniform density, and because gases don't have uniform density, those laws, those principles, will not apply to gases. Going back to Audrey, number 6, does something weigh more in air or in a vacuum, and why?
Something will weigh more in air than in a vacuum because air has total density and a vacuum has no air pressure.
Kendall?
Something can weigh more in air than a vacuum because in a vacuum there's no air pressure.
Well, okay, I see what you're saying. The object itself will weigh more in a vacuum. Because just like in water, you know how you weigh less in water because the water's lifting up on you with buoyant force? There is air lifting up on you with buoyant force. It's just you weigh too much for the little bit of buoyant force to actually lift you, right? You displace a certain amount of air. And however much air you displace, Michael, is that much more buoyant force acting on you in a sense. Kendall doesn't displace as much air. She doesn't get as much buoyant force, okay? But, so if you were to weigh yourself in a vacuum, you don't get any of that buoyant force. Again, I'm using the term loosely. We don't normally call it buoyant force, but that atmospheric pressure that also lifts up. And so technically you would weigh more in a vacuum. Your weight is offset technically by the weight of air you displace. So when you look at the scale, you're like, oh, I weigh this much. Well, that's in air, but if you were in a vacuum, you weigh slightly more. All right, number 7. How might Bernoulli's principle explain the operation of a parasail? And I realize, if they don't know what a parasail is, then that doesn't make any sense. How many know what parasailing is? How many say, I don't even know what a parasail is? Okay, so Audrey, explain to the class, what is parasailing, or what is a parasail?
Well, you take this boat, and you go really fast in the boat, then there's this contraption thingy that looks like a, I forget what it's called.
A parachute.
Yeah, a parachute. And you start out on the water, and then they go really fast, and then you get up into the air because of all the drag.
Yeah, so a parasail is basically like a parachute, but instead of jumping out of a plane, you start on the back of a boat, and as they go faster and faster, the air begins to fill the parasail, and so it basically, it takes up space, which gives you a little bit of lift. The drag gets you a little bit of lift, and also the curvature, and this is where kind of thinking about what the book talks about with Bernoulli's principle, kind of like an airfoil, as you're getting that air to go over the top of the parasail because of the curvature, just like a parachute. As the air goes over the top, that curvature makes a little bit more of a speed up effect, and underneath you don't get that, so that allows you to get that lift, as the book had talked about. I realized as I was looking over the question, I'm like, unless they knew what a parasail is, because the book doesn't describe a parasail, they're not going to have a clue what it's talking about. Number 8, describe horror vacui, or however you pronounce it. Kendall, we'll give this one to you for no good reason.
Horror vacui was taught by Aristotle that in a vacuum it is impossible to create because nature immediately fills up any empty space with the nearest matter it can find.
Okay, I'm not sure about quite the way you phrased it in one spot, but yeah, basically the idea was nature abhors a vacuum, so you can't actually make a vacuum. Because if you made a vacuum, nature would fill the vacuum with something, air, liquid, something would rush into the spot. Number 9, how did Tortelli explain the rise of water in a water pump? Michael?
Tortelli explained the rise of water in a pump by showing how when you pump, a vacuum is created and atmospheric pressure forces the water up into it.
There we go. The pump basically was creating a vacuum, and so the thought was, horror vacui, nature rushes in to fill the vacuum. Well, no, it's atmospheric pressure that pushes the water up to fill the vacuum. Number 10, what height of water is supported by atmospheric pressure, and what height of mercury, Audrey?
32 feet of water is supported by atmospheric pressure, and 33.9 feet is the height of mercury.
Oh. So atmospheric pressure can support more mercury than water. Those two numbers you gave were in the text, but we got a little confused on them. Kendall, can you help her?
I got 32 feet of water and 760 millimeters of mercury.
All right, we're right on the 760 millimeters of mercury. Where did she get the 33.9 feet from? Because it wasn't mercury. Do either of you remember from your reading?
It's the actual water.
It's what water actually could be supported. 32 feet was what Tortelli said it was, because his pumps didn't have a perfect seal, so water was only able to rise about 32 feet in the water pump. That's what he assumed it was. Later we found that, okay, if all things being perfect, 33.9 feet of water is actually supported, and then 760 millimeters of mercury. Again, a lot less mercury because it's so much heavier, so atmospheric pressure can't hold as much. Number 11, how did Pascal confirm Tortelli's conclusion that mercury is supported at a height of there's the answer, number 10, is supported at a height of 760 millimeters by atmospheric pressure? We did story time with Kendall last time. Let's see, because this is a little bit of a story time. Story time with Michael.
Pascal confirmed Tortelli's conclusion by testing the atmospheric pressure on Mercury at different height levels on Earth.
Very good. And that was a paraphrase, wasn't it?
Yes.
Right? As opposed to stating directly from the book. Anyone happen to get down where he went to try to test this thing? Okay, so he went to the top of a tall building and really didn't notice anything. And then he went
to a mountain.
To a mountain. And then he noticed, okay, there is an effect here, so we see what we should expect. And number 12, what is standard atmospheric pressure? There's several answers that you could give here. Kendall?
Standard atmospheric pressure is 118.
Okay, that's one answer you could give. There are several answers we could give. Anyone else give more or different answers than just 1.00 atmospheres?
It is enough pressure to support 760 millimeters of mercury at 0 degrees Celsius.
Okay, so 7, okay. Do you have anything else? Okay, there's a few other things, 14.7 pounds per square inch, 1,013 millibars, 1.013 E5 pascals, 760 torr. There's a lot of different ways to describe standard atmospheric pressure. All right, I mentioned this just a moment ago, but the 14.7 pounds per square inch, we saw some videos yesterday. If you watched on YouTube, you saw some videos that they were watching in class demonstrating the strength of atmospheric pressure. And we said every square inch at sea level that's exposed to air experiences almost 15 pounds of air pushing on it. And we said, why don't we notice this air pressure? Why do we seem oblivious to this atmospheric pressure? Michael?
We're built different.
We're built different, okay. That's one way to put it, I suppose. Kendall? For instance, the book even gives the example, I used it yesterday, you would try to lift this up, well, I've got 15 pounds on every square inch of my hand. Okay, why isn't that an impressive feat?
Because it's like coming in all directions.
Yeah, it's all directions. So I have 15 pounds pushing down, but I also have 15 pounds per square inch pushing up, right? And so we don't really notice it. Also, God made our bodies to handle that pressure all over us. You say, we're being squeezed to death. Well, God made our bodies to handle the squeezing, right? And just as he made some fish to handle squeezing at great depths of the ocean, he didn't make us to handle that. Well, he made us to handle this. And we talked about that yesterday. We said if we were to go up to space without anything, just dressed as you are, somehow your body could just rise way out into outer space. What would happen as you rise, Michael?
You get bloated.
You begin to expand, you get bloated, and then eventually pop. And then there's messes, scattered, space debris everywhere, okay? Because we aren't designed to be in a place where there is no air pressure. We need that atmospheric pressure on us. What do we call the empty space where there is no gas, no matter, just nothingness? That's called a vacuum. Of course, we created partial vacuum in our soda can yesterday. And we're working on a couple of these. Audrey didn't get to do it yesterday for those watching on YouTube. So we did the soda can thing. And so right now we are boiling water in a couple of soda cans. And basically the premise here, Audrey, as you read in your homework reading, is that as the water is boiling in the soda can, vapor is coming out. And the vapor, as it rises, pushes the nitrogen, oxygen, air out of the can. But there's still water vapor, which is still a gas. So there is still this gaseous pressure, this air pressure in the can, on the can, so everything's good. But I'll use my can over here. But if I were to take, I think it's been boiling long enough, probably. If I were to take my can and if I just flip it upside down like this, and okay, there it slowly goes. Okay, it didn't do very well. I think I'm going to let yours boil a little bit longer. But as I dunked it into the cold water, I think I'll actually not pour it out in there because that'll make the water hot. I'll pour it out into the sink here. But as the water flows out, right, it still has that vapor inside, but because the bowl of water has some cold water, and there's no ice left, so it's not as cold as it was yesterday, apparently. Remember yesterday, there was still ice floating in it. That might be part of the problem. I think mostly I just didn't let it boil long enough. But as it touched the cold water, that causes condensation. If you watch the videos on YouTube, you actually saw one where a guy took a can of paint thinner, those metal cans of paint or stain or whatever, filled it with water, boiled the water in there, and he sealed it off. So nothing could escape, and he just spritzed it with a spray can of cold water. And again, it just caused condensation for the steam, and as it did, slowly that can began to get crushed. I'm not close, but I have one of those. Anyway, so we're going to let yours boil for just a little bit longer there, Audrey. But again, it creates this absence of air in the can as it condenses. Let me see, just see how cold it is. It's still pretty cool. I'll let that boil a little longer. And as we saw the effect of atmospheric pressure here, the effect was rather minimal. I mean, that's really not a very good crush. So hopefully yours will crush better. That or Fago makes their cans really strong, but I don't think that's the case. I'm pretty sure I just needed to let it boil a little more and push all that air out. We talked yesterday about a couple of principles, or we looked at one principle that we talked about with liquids that I said also applies to gases. And we've alluded to it already in the homework, but class, that is Archimedes' principle. Again, some of the principles don't carry, right? The principle of continuity, right, where liquid flows through different pipes and has to narrow down, and as it narrows down to get the same volume through, it has to move faster. Well, to an extent that will work with air, to another extent not as much, because air can just compress down. It doesn't necessarily have to move faster. So the math at least doesn't work perfectly. You know, the basic concept is still there. As air is compressed into a smaller opening, it will speed up, but it's not the same, you know, diameter squared times velocity perfect relationship that we would see with an ideal liquid. We also looked at, we said the law of liquid pressure, depth, you know, affects the pressure. Well, to an extent that's true. Certainly Pascal's principle doesn't apply, right? Because you can compress a gas where you can't compress a liquid. So as you push liquid in a hydraulic device, now, they do make pneumatic devices, air brakes, for instance, on buses and large semis, okay, use compressed air, but that's a little different. It's also why it requires a CDL. And there's another example, by the way, of a hydraulic device, right? The brakes on a car, right? Your brake fluid, you push on the brake, which pushes this little piston in. And that little piston pushes liquid out larger ducts to where the brake calipers are, and it squeezes them, pushes them up against the disc on the car and slows the car down, right? You put a little bit of force, it puts a whole lot more force up against the wheels of the car to slow the car down for you. And wears out your brake pads if you do that too often. But Archimedes' principle, well, that we don't really care about the fact that a gas is compressible. Like water or like liquid, you still have this ocean of air around us that provides, as we said, upward force as well as downward force. So the more space something takes up, the more buoyant force is acting on that object. Now, it's not much. I mean, seriously, if you took a Mr. Nadaski-sized bit of air, how much would it weigh? Not nearly as much as Mr. Nadaski, right? Now, the pressure would be there, but the actual weight of the air would be negligible. And so I don't have a whole lot of buoyant force acting on me. But for instance, if you were to jump out of a plane with a parachute, now you're taking up all this extra air and you're getting all that extra lift. Okay, that helps to slow a person down, helps them hopefully glide to safety instead of, you know, splat, which is a bad day, right? Also, we said there are some things that, again, dealing with Archimedes' principle, Audrey, going back to liquids, we said what determines whether or not an object floats in a liquid? Density. Well, in the same way, that determines what will float in air. We said that there are a couple of key elements from the periodic table that have a density much less than nitrogen and oxygen. And what would that be, Audrey? You can look at the periodic table if you need to. There's some things that have a lower density, lower atomic mass than nitrogen and oxygen.
I was under instructions to deliver cookies from Miss Christy Henderson. Okay. I'm not here. All set with
If there is one. Okay. Sorry, Audrey?
Nitrogen.
And certainly the lowest one would be way over here with hydrogen, right? That's got the absolute lowest atomic mass, right? So therefore the lowest density. Other gases maybe we see here? I mean, like the lithium, beryllium, those aren't gases. Boron, not as much a gas. Carbon, not a gas. Nitrogen, oxygen are helium, right? And that's why we use helium balloons, right? The density is just less. They weigh less, and that's why we fill balloons with helium. We said yesterday, why not hydrogen? Any idea from chemistry? Something special about hydrogen, Kendall? It's very flammable. And so we don't want to make hydrogen balloons because, you know, poof, go boom. And but helium balloons, certainly, they float because with their lighter atomic weight, they displace more air than they weigh, even with the weight of the balloon. Now, you blow air into a balloon, the air in the balloon weighs the same as the air it displaces, but then you have the weight of the balloon itself, and that causes it to slowly fall. Hot air balloons, we said yesterday. You heat the air expands, it takes up more space, it becomes less dense, so it rises, if you have enough of it. And if you have enough of it, it can lift a person off the ground or people off the ground, and so flight was achieved through lower density, as you alluded to earlier. We also want to look at Bernoulli's principle, and this one I think is kind of interesting the way it applies to gases. Bernoulli's principle, remember, Bernoulli said that as the velocity of a fluid, we said earlier liquid, but as the velocity of a fluid increases, the lateral pressure decreases. A couple of interesting demonstrations here I can show you with this, then I'll have you write some things down in your notes. But right now, if I just try to hold a piece of paper out like this, if I curl the paper, I can give it a little bit of structure to help it to stay up. But if I don't, it just kind of falls down. Why? Well, it has weight. There's air pushing up on the underside, but there's also air pushing down, and those two offset, so then the weight of the paper causes it to fall. But if I blow across the top of the paper, it lifts the paper up. Why? Well, because as the air comes out of my mouth, it speeds up, right? The air was just kind of there, and all of a sudden it begins moving this way. Well, as the air is moving this way, the lateral pressure decreases, right? In this case, since the air is going this way, lateral is actually up and down. Does that make sense? So the downward pressure decreases. Well, as the piece of paper hangs here, the upward pressure hasn't changed, just less downward pressure. You could also think of it as blowing the air molecules off the top of the paper. Well, now the air that's up here is all going this way, so air is able to lift up underneath the paper. Does that make sense? A similar demonstration could be if I take two pieces of paper and I blow between them. Again, you would think, if anything, blowing between them would push them apart. But watch. I curl them outward there. When I blow down between them, they actually attract together. Why? Well, we've got the two pieces of paper, and as I blow downward, now the lateral pressure is sideways. Limited lateral pressure. But the pressure on the outside hasn't changed. And so since the pressure on the outside is stronger, it pushes the papers together. Does that make sense? Again, you could think of it as I'm pushing the air out from between them, which creates a vacuum. Well, not really. I'm actually blowing more air molecules, aren't I? I'm just making them move faster, and so that pushes the paper back together. Does that make sense? Questions on that? All right, so there's another interesting demonstration, and I stole a hairdryer. I do not use this hairdryer myself. I don't need to. But stole this hairdryer here. And this is a cool thing that you can do at home, Michael, since you have a sibling who would use a hairdryer perhaps. And if you can get her to let you use it. And then ladies, I assume you have hairdryers. Okay, so anyway, some hairdryers don't work as well. My wife's hairdryer actually doesn't work particularly well. So I borrowed this one from a fellow teacher who has a cool hairdryer. It even has cool air. But it blows really well. And so as I turn on the hairdryer, let me turn it down low a little bit. The hair, obviously you've got this column of air being blown upward, correct? But really, truly, my hand right here, I feel nothing until I get right here. Then I start to feel the air moving. Right, so there's this just a narrow column of air rising. Everything else is pretty much the same. Well, what this means is that the pressure right here, the air is moving this way, but the outward pressure is less. Well, the pressure around this narrow column of air hasn't changed at all. And so the ping pong ball, it obviously is blown up, right, by the atmosphere, by the air that's being blown, but it's also being held in place. There's this column of air surrounding it that holds it in place. So now let's see. And so it just follows because there's this wall, if you will, of air pressure around it. Let's see if I can get it to go here. Okay, and then it falls. Okay? See if I can go the other direction with it. But again, it's just this column of air and the air pressure around it. Now, obviously, the ping pong ball has weight, right? So as I begin to turn it, the question is which wins? The weight of the ball to pull it down, or the air pressure surrounding it that's holding it up? I don't know, I think this blue button is supposed to make it cold, but it's still pretty hot. Alright, so let's see what we got here. Slowly okay, I mean, you saw, I mean, we're at, what is that, maybe a 30-degree angle, right? It's just a really neat demonstration to see how strong the air is surrounding that narrow column of air. I'll let you guys play with this here in just a minute when we go off camera. But anyway, this is a fun thing that you can do at home if you happen to have ping pong balls, and of course everybody's got a hairdryer apparently, if your hairdryer is good enough. Okay, if your hairdryer is not good enough like my wife's, because I'm a cheap husband and apparently don't buy her cool hairdryers like this Infinity Pro by Conair with twistable handle for compact storage in luggage. Yeah, and it's shiny red. All right, anyway, what?
It's bougie.
Apparently. All right. Anyway, so this brings us then to what the book talks about, which is a really interesting discussion. And be honest, it's one that's got scientists arguing with each other, and that's this concept of flight. For a while, it was believed what the book teaches, that the shape of the airfoil and the application of Bernoulli's principle is what actually allows an airplane to get off the ground. The idea is that an airfoil, or a wing in general, has a relatively flat underside, and then the curvature of the front is such that the air, as the plane moves quickly, like relatively the air molecules fly at it quickly, right? You felt this, you ride a bike, right? The air is not blowing in your face any harder, but relatively it is, correct? Because you're hitting the air quicker. So the idea is that as the wing hits the air, this shape forces most of the air over the top. And then some air is left undisturbed across the bottom. Well, as you're trying to force more air over the top, you're compressing it. Now, the principle of continuity, which we already said doesn't apply perfectly, and this is why scientists argue, but the principle of continuity would say as you're forcing it more air, again, because you still got this air trying to go here too, you're forcing more air over the top, it forces it to speed up. And as it speeds up, the lateral pressure decreases. But the pressure underneath, since you don't get that same disturbance under the wing, the pressure underneath is greater, and so the plane gets off the ground. Again, it's not a huge drop, but let's take Bernoulli's principle, and let's say that the speed up is marginal, very slight. Should still be somewhat greater, even though the principle of continuity doesn't hold perfectly true in a linear sense. If it decreases at all, let's say underneath we've got 14.7 pounds per square inch at liftoff, right? Once we get up higher, it's going to be less than that. And let's say that above the wing we have, let's just say 14 pounds per square inch. That's not an appreciable drop, right? But you think about how many square inches are on the surface of a wing, right? They're long, they're big. So at that point then, okay, maybe there's enough to get it off the ground. That's what some people believe, and that's what the book teaches. That idea has been rejected for a couple of reasons. One of them, again, is the fact that it's hard to really calculate how much the speed up of air actually occurs. The other idea is this: with a helicopter, well, it doesn't have an airfoil; it has a propeller, which doesn't have this shape necessarily. So the next thought was, well, we know this, that the blades of the propeller on a helicopter are not flat, they're angled, right? This is the difference between toy helicopter you played with as a kid and real helicopter that actually flies, is the blades have to be rotated slightly, correct? And as they're rotated slightly, well, that's not too different from as the plane is taking off, trying to get this angle of attack to develop at takeoff, and that is that the front of the plane comes up just a little bit. Well, in that case, just like the blades of a helicopter, as they're chopping, right, as they hit the air is forced downward by the blade, right? Like drag in a sense, I suppose. And law of action, reaction that you talked about, Newton's third law of motion, which we'll look at more. If the air is forced down, then you force enough air down, that's going to force the helicopter up. Well, could the same thing then be true with the wing of the airplane? Okay, air force down, plane goes up. Okay, so there are some people who say, no, it's just Newton's third law, It's not Bernoulli's principle at all. There are some other people that say, well, because of the angle of the plane and because of the shape, the air as it goes over tends to go more straight line, and as it does, it kind of sucks the air here along with it. Something called entrainment we'll look at later in the chapter. And so as it does, it creates not a perfect vacuum on the back end of the wing, but it creates a little bit of a vacuum on the wing. Well, again, that means there's no pressure back here. There's pressure here. That lifts the plane up. So there's a few different lines of thought, and frankly, nobody's come out with anything conclusive. You just get these three arguments. I'm not a physics expert. I'm a physics teacher, but I'm not a physics expert. I don't devote my life and time to studying it. I would tend to say it's probably a combination of the three. We get a little bit of the acceleration over the top. I could certainly make the case for that. We could also make a case for entrainment, and we create a vacuum also as the plane is flying this way too, right? As the plane is flying, if it's angled properly, it's just going to be pushing the air forward, and of course the air is going to rush over there. Even if it didn't suck the vacuum out, it would still create a little bit of a vacuum behind the wing. Again, not a perfect vacuum, but a little bit of at least a low pressure area, so you get more pressure on the underside. And yeah, the third law of motion also makes a whole lot of sense as well. By the way, this angle of attack also does explain the same thing. Blade chops around, low pressure area created, so it explains helicopter and airfoil at the same time. You just need to know there's three explanations. Okay, so in your notes, let's go and get just kind of a quick synopsis down for flight. Three ideas. Flight, three ideas. And I'm curious to see what the next physics books will say. Okay, so because for years they've been saying this, and we're starting to change our minds. So you look at the NASA website, they actually ignore Bernoulli's principle. They look at the other two only. So the three ideas, number one, Bernoulli's principle. Air speeds up over the top, which decreases pressure on top. Air speeds up on top, which decreases pressure on top. And that's what the book teaches. Air speeds up over the top, which decreases pressure on top. That's one idea. Idea number two is because of the angle of the wing and the shape of the wing, a low pressure area is created. It has nothing to do with the speed of the air, it's just that a low pressure area is created, which results in lift. Idea number two is the shape and angle of the wing creates a low pressure area, or near vacuum, which results in lift. And idea number three is Newton's third law. Air is pushed down, airplane goes up, or helicopter if we want to go that route. Airplane goes up because air is pushed down. And for reaction, there's an equal and opposite reaction. Push enough air down, it pushes plane up. Three thoughts on flight and how we attain it. All I know is it's a nice thing airplane gets off the ground. There's another application to Bernoulli's principle that is not as argued amongst people. If you're turning over a page, what is that, 54, Kendall? One more page over, 54. And that's the golf umbrella. Now, I went to college at Pensacola Christian College, and in Pensacola, I think because of the ocean breezes, rain does not fall down in Pensacola. Rain blows sideways. Not perfectly sideways, except during hurricanes, but it's definitely at an angle. And with the air that comes whipping, the bigger umbrella, the better, okay, for one thing. For another thing, as the air comes whipping along, the curved shape of the umbrella does force air to go over the top of the umbrella. And you've already got the air moving relatively quickly anyway. Now, as it just comes here, it's not going to be pushed over, it's going to go underneath. Well, again, Bernoulli's principle would say if more air is pushed over, you're going to get a faster movement of air, which means less pressure. And so I've seen this happen way too many times. You're walking to class across campus, and your umbrella just flips up. Anyone ever had an umbrella invert? Now, it will do that as well if the wind is blowing this way, and you hold your umbrella like this. Well, obviously, you're just asking for the air to open it up. But even if you hold the umbrella straight, with air moving like that, again, it can still whip over the top of the umbrella and invert the umbrella. So there's two solutions. One is aim the umbrella into the wind, which is the easiest way to go anyway. Except when you're walking around buildings and the air changes directions at times. And you're trying to gauge where's the wind coming from, and sometimes you're still wrong. The other is to get something called a golf umbrella, which are huge umbrellas that actually have two layers that are supported, and the top forms a flap that hangs over the sides. So there's a space that air can go through the umbrella. And you see the picture there with the green umbrella. Okay, you've got the air, and it is able to go through the middle of the umbrella. And by going through the middle, that's less air to go over the top. So where we do see a little bit of a lift is at the top flap of the umbrella, but it hangs over the sides enough, the rain still doesn't get on you. And so after a couple of years, I finally invested in a golf umbrella and wrote "Thou shalt not steal" on all the white parts, because people are forever, oh, there's an umbrella, let me take that one. It is not yours. Do not take my umbrella, because then I have no umbrella, or I'm forced to resort to thievery in kind, and that's sad also. All right, anyway, questions on Bernoulli's principle. Again, as air speeds up, pressure drops. And we saw some conclusive demonstrations, then a couple of, especially with the flight, maybe a little bit more theoretical. Questions on that? All right, we may come back for another part of the video. I think we're probably going to end here. We're going to be doing some things here in class that we won't be able to get on camera. Homework for this evening, if you write this down, read pages 55 to 62. Read pages 55 to 62. On page 67, just 3 questions for the 3-day weekend. 3 questions, that's numbers 14 through 16. Page 67, questions 14 through 16. And we'll take a look at that probably in our next lesson. We will see.